In this video, we're going to go over the SN2 reaction mechanism. So in this reaction, we have a nucleophile reacting with the substrate. The nucleophile is hydroxide. It has a negative charge, and the substrate is the alkyl halide. Bromine is more electronegative than carbon. So bromine bears a partial negative charge, carbon bears a partial positive charge. So the nucleophile is attracted to the partially positive carbon atom, and so it approaches it from the back, and as it attacks the methyl group, the bromine group gets expelled, and so we get the product, which is methanol, and we also get a side product, also known as the leaving group, which is the bromide ion. And so that's the basic idea behind the SN2 reaction mechanism. To draw the transition state, it looks like this. So here we have the 3 hydrogen atoms attached to the carbon, and we have a bond being created between the oxygen and the carbon atom, and a bond that's breaking between the carbon and the bromine atom. And so the transition state looks like this. Carbon bears a partial positive charge, bromine bears a partial negative charge, and the same is true for hydroxide. Now let's go over some other reactions that is associated with the SN2 mechanism. What do you think the major product for this reaction will be? Let's say if we have butyl bromide and we wish to react it with sodium methoxide. Now what you need to realize is that the sodium ion is a spectator ion, so it's not going to do anything in the reaction. The nucleophile is the methoxide ion, and so what it does is it attacks the carbon from the back, that is away from the bromine atom, and then it expels the bromine atom. Now it doesn't want to attack from the front because bromine has a partial negative charge and the oxygen atom has a negative charge. So if it tries to approach from the front, it's going to be repelled by the electronegative bromine atom. So instead, it attacks from the back. Therefore, we're going to get this product, which is an ether. Now let's work on some other examples. Let's say we have, in this case, 2-bromobutane, and let's react it with potassium iodide in acetone. Acetone is a polar aprotic solvent. There are no OH or NH bonds. And it turns out that polar aprotic solvents, they enhance SN2 reactions. What do you think the major product for this reaction will be? So first, we need to identify the nucleophile. The nucleophile is the iodide ion. And so what it's going to do is it's going to approach the carbon from the back, expelling the leaving group. Now notice that we have a chiral center. And notice that the bromine is on the wedge. So now, because the iodide ion approached from the back, it's going to be basically on a dash. So this means the bromine atom is coming out of the page, and the iodide ion, or the iodine atom, is going into the page. And so this is the product of the reaction. For an SN2 reaction, we get inversion of configuration. So as you can see, the stereochemistry changes. This was R2-bromobutane, and now we have S2-iodobutane. Now here's another example. So let's say we have the chair conformation of 1-bromo, 3-methyl cyclohexane. Let's say the methyl group is in the equatorial position and the bromine atom is in the axial position. Draw the major SN2 product for this reaction. Let's use sodium cyanide in DMSO, dimethyl sulfoxide, which is another type of polar aprotic solvent that enhances an SN2 reaction. So go ahead and predict the major product for that reaction. So we know the cyanide ion, which looks like this, it's basically a triple bond between the carbon and the nitrogen atom, but the carbon atom bears the negative charge, so it's the nucleophilic center. It's going to attack the carbon from the back, expelling the leaving group. Now, because the SN2 reaction proceeds with inversion of configuration, the cyanide group is going to be on the equatorial bond because the bromine atom was on the axial bond, and so you need to switch it. And so the product, let me put over here where I have more space. The product will look like this. So the methyl group is unaffected, and now cyanide is in the equatorial position. And so this is the SN2 product for this reaction. The SN2 reaction is a second order nucleophilic substitution reaction. The rate of the reaction depends on the concentration of the substrate and the concentration of the nucleophile. So if we double the concentration of the substrate, the rate will double. If we triple the concentration of the substrate, the rate will triple. If we double the concentration of the substrate and double the concentration of the nucleophile, 2 times 2 is 4, so the rate will increase by a factor of 4. If we triple the concentration of the substrate, quadruple the concentration of the nucleophile, the rate will increase by a factor of 12. So it's first order in the substrate, first order in the nucleophile. Overall, the rate is second order if you add 1 and 1, which gives you 2. Now the energy diagram for the SN2 reaction looks like this. There's only one transition state, so here it is. This is the energy of the reactants, this is the energy of the products, and on the y-axis we have the energy. On the x-axis we have the progress of the reaction. The activation energy is the difference between the energy of the reactants and the transition state. Now it's important to understand that the SN2 reaction is a concerted reaction mechanism. Everything happens in one step. All the bond making and bond breaking processes occur together, and so it's a concerted reaction mechanism. Now here's a question for you. Consider the following alkyl halides. Which of these alkyl halides is most reactive in an SN2 reaction, and which one is the least reactive? Feel free to pause the video and answer that question. So here we have a secondary alkyl halide because the carbon that bears the bromine atom is attached to 2 other carbon atoms. And in the middle we have a tertiary alkyl halide because that carbon, which is here, is attached to 3 other carbon atoms. And on the right, we have a primary alkyl halide because the carbon that bears the bromine atom is attached to only 1 other carbon atom. It turns out that the primary alkyl halide is the best for an SN2 reaction, whereas the tertiary alkyl halide is the worst. And the reactivity is as follows. A methyl alkyl halide is better than a primary alkyl halide, which is better than a secondary alkyl halide, which is better than a tertiary alkyl halide. Now let's talk about why a tertiary alkyl halide is bad for an SN2 reaction. So I'm going to use tert-butyl-bromide as an example. Now in order for the SN2 reaction to take place, the nucleophile, let's use iodide as an example, the nucleophile has to attack the carbon that bears the bromine atom. So it has to attack this carbon. But it's not easy to attack it because these 3 bulky methyl groups, they basically provide a barrier against the iodide ion. And so it's very difficult for the iodide ion to attack that carbon with those 3 methyl groups being in the way. And so that's why the SN2 reaction virtually doesn't occur with tertiary alkyl halides. It's too sterically hindered. And so the reaction rate is very, very, very slow. Once in a while it may happen, but for the most part it's negligible. So tertiary alkyl halides for the most part do not react in the SN2 reaction mechanism. Now compare these two alkyl halides. Which one is more reactive in an SN2 reaction? Is it the one on the left or the one on the right? Now this carbon atom is a secondary carbon, and the same is true for that one. So the substitution is the same, but which one is going to work better? On the right, we have something called an aryl halide. You need to know that the aryl halide does not work well for an SN2 or an SN1 reaction. And the reason being, in order for the SN2 reaction to work, the iodide ion has to attack this carbon. However, the pi electron cloud of the benzene ring prevents that from happening. And so the iodide ion can't approach from the back to attack that carbon due to the pi electrons. So aryl halides do not participate in the SN2 reaction. Therefore, this one is better. And the same is true if you compare, let's say, a vinyl halide with an allyl or an allylic halide. The vinyl halide doesn't work. So if your leaving group is directly attached to a double bond that is in the ring or on a double bond like this, it's not going to work. So this doesn't work too well for the SN2 reaction. Because once again, the nucleophile has to approach from the back, and the pi electrons, they interfere with that. The pi electrons have a negative charge, and so they repel the negatively charged iodide ion. So this is not going to work. So the allylic halide works a lot better than the vanillic halide. Now here's another example for you. Consider these three alkyl halides and determine which of these three is the best for an SN2 reaction. Now this carbon is a secondary carbon, and this one is also secondary, and this one is secondary. So how can we determine which one is better for an SN2 reaction? In a situation like this, look at the adjacent carbons. On the right, all of these carbons are primary, so there's no difference here. But on the left, this carbon is secondary, this carbon is tertiary, and this carbon is quaternary. Just by looking at this, a secondary alkyl halide is better than a tertiary or a quaternary one. So even though we all have secondary alkyl halides for this example, if you look at the adjacent carbon, a secondary carbon is less sterically hindered than a tertiary or quaternary one. So this is going to be the best for an SN2 reaction. Now, it's easier for the nucleophile to approach this carbon rather than to approach this carbon, because that quaternary carbon has a lot more methyl groups than the secondary one, and so this alkyl halide is more sterically hindered than this one. So it's easier for the nucleophile to attack this particular alkyl halide. So if you have alkyl halides with the same basically substitution, look at the adjacent carbons and see which one is less sterically hindered, and the SN2 reaction will work better for that one. So this alkyl halide is the least sterically hindered, which means the carbon is more accessible to a nucleophilic attack, and that's why this one works the best. Now here's another question for you. So let's say if we have 1-bromobutane reacting with hydroxide compared to 1-bromobutane reacting with water. Which reaction will proceed faster in an SN2 reaction? Is it the one with hydroxide or the one with water? So the substrate is the same. In both cases, they're primary alkyl halides. So the difference lies in the nucleophile. If you recall, for an SN2 reaction, the rate depends on the substrate and the concentration of the nucleophile. So the strength of the nucleophile is important. So which nucleophile is stronger, hydroxide or water? Because hydroxide has a negative charge, it's a stronger nucleophile than water. Therefore, the first reaction will work faster in an SN2 reaction. So this reaction is better because hydroxide is a stronger nucleophile than water. On the periodic table, we have elements such as carbon, nitrogen, oxygen, and fluorine, and then below that chlorine, bromine, and iodine. So going towards the right, nucleophilic strength increases. So for instance, NH2 minus is a stronger nucleophile than OH minus, which is stronger than fluoride. Now, in a protic solvent, a good example of a protic solvent would be like water or methanol. So you can write methanol as CH3OH. Sometimes you might see it as MEOH, or ethanol, CH3CH2OH, or ETOH. So typically in a protic solvent you'll see hydrogen bonds. In a protic solvent, nucleophilic strength increases going down the periodic table. So what that means is that iodide is a better nucleophile than bromide, which is better than chloride, and which is better than fluoride. To keep things short, fluorine, or rather the fluoride ion, is a stronger base than iodide. But in a protic solvent, it forms hydrogen bonds with water and methanol. And so it stabilizes fluoride, which means that it's less accessible, or it's less able to behave as a nucleophile because it's solvated by the solvent. The solvent stabilizes fluoride because it's a better base. Iodide, being a weaker base, is not stabilized by the solvent as much, and so iodide is free to behave as a nucleophile in a protic environment. And that's why iodide works better than fluoride, even though fluoride is a stronger base than iodide. It's because the solvent stabilizes the fluoride ion, and so it's not free to behave as a nucleophile. Iodide, being a weaker base, is not held back by the solvent, and so iodide behaves as a stronger nucleophile in a protic environment. Now, in an aprotic solvent, the situation is different. Nucleophilic strength is the same as base strength. So in an aprotic environment, fluoride is a better nucleophile than chloride, which is better than bromide, which is better than iodide. So let's say like acetone. That's a polar aprotic solvent. As you can see, there's no hydrogen bonds in acetone. And so if you were to dissolve, let's say sodium fluoride in acetone, all of the acetone molecules will orient themselves towards, let me draw this better. All of these acetone molecules will orient themselves towards the sodium cation. Sodium has a positive charge, and the oxygen atoms, they all have a partial negative charge. And so they're going to stabilize the sodium cation. Now the fluoride ion is not held back or solvated by the polar aprotic solvent, and so and it's also not held back by the sodium ion. So therefore the fluoride ion is free to react, and so this enhances the potential energy level of the nucleophile. And because it's free to react, it's going to behave as a stronger nucleophile. And that's why polar aprotic solvents work very well for SN2 reactions. Polar protic solvents like water and methanol, they work better for SN1 reactions. And so keep that in mind. So for SN2 reactions, you want to use a polar aprotic solvent because they enhance the strength of the nucleophile. They solvate the cation, allowing the nucleophile to be free to react. And remember, fluoride is better than iodide in the aprotic environment. In an SN1 reaction, it's best to use a protic solvent. And in a protic environment, iodide is a better nucleophile than fluoride. Now let's work on some example problems. Let's say if we have 1-bromobutane, what is the major product if we react it with water? So feel free to draw the SN2 product of this reaction. Now water is going to behave as a nucleophile, attacking the carbon atom, expelling the leaving group. And so that's the basic idea behind the SN2 reaction. But this reaction occurs in 2 steps. The first step is an SN2 reaction, and the second step involves deprotonation of the hydrogen. Now when water attacks the carbon, it behaves as a nucleophile. However, when water abstracts a proton, it behaves as a base. So water can behave as both a base or a nucleophile. And so the end result is that we get an alcohol, 1-butanol. And so that's how you can convert an alkyl halide into an alcohol. Now let's look at another example. Let's say if we have an alcohol and we wish to react it with hydrobromic acid, what's going to happen? So this too will also be an SN2 reaction, but the first step will be protonation. The oxygen is going to grab a hydrogen from the acid, kicking out the bromine atom. And so right now, the OH group has been turned into a good leaving group. In this form, the OH group is a bad leaving group because let's say if you try to take a nucleophile and kick it out, you're going to get a hydroxide ion, which is a strong base. And the strong base is not stable. And so strong bases are bad leaving groups. But if you protonate the alcohol, put a positive charge on the oxygen, then it becomes a good leaving group. So now bromide can attack from the back, expelling water. And water is a stable base. And so water is a good leaving group. And so this gives us the original alkyl halide. So that's how you can convert a primary alcohol into an alkyl halide using an acid.